Colorimetry is a way of measuring the concentration of solution, which you can do if the compound is colored, right, or absorbs light. So what I've tried to draw here is it's supposed to be got some copper sulfate in there, which is blue due to the presence of the copper 2+ ions. And if we shine white light, okay, so there's white light. White light is, of course, made up of all the colors of the spectrum, which I've drawn here. Now the copper sulfate solution, it looks blue because it absorbs most of the red, the orange, the yellow, and it only lets through these blue and green colors. Okay, so it's going to, that's why it looks that color. Now, so in colorimetry, the light absorbed is proportional to the concentration. All other things being the same, like the path length of the light and so on. So a basic colorimetry is this top diagram. So if you shine white light, goes through the solution, and then you have a detector, a light detector there. Now there's a problem if you did it this way, is because the detector kind of gets swamped by the green and the blue light which passes through the solution. We're really only interested in the wavelengths, the frequencies that are absorbed by the solution. So we're interested in how much red and orange and yellow and or violet is absorbed. So if you do it without a filter, it doesn't work very well. Okay, so what you do there is you put a filter, a color filter in there. Now you have to choose the color of the filter sensibly. We know that our copper sulfate solution is going to let through blue and green. So we want a filter which is going to block blue and green light. So if you picked up a piece of colored cellophane plastic, used as a transparent piece of plastic, which you'd use as a filter, and it looked green, that would be no good in this case, because it would be letting through the very wavelengths of light which are swamping the detector here. So you want to block those out. So in this case, that filter would appear to be red. So it would look like a piece of red cellophane. And the reason why it would look reddy orange is because the only colors it's letting through are these red and orange wavelengths, red and orange frequencies. It's blocking out, importantly, the green and blue, but it's also blocking out the violet, so that doesn't really matter. So you can see there, it's just letting through those red and green, and they're the ones which can be picked up by the detector. Now you can see there that the less light on the detector, the less light, that means the more concentrated the solution is. Okay, so that's how it works. But before we can measure the concentration of a copper, like for example, we're saying copper sulfate here solution, we need to construct a calibration curve. So what we've got here is I've got 8 tubes, and this one here, the first one, the concentration of copper sulfate would be 0, so that would just be distilled water, and then we could go up like a mole per decimeter cubed. 0.1, 0.2, 0.3, 4, 5, 0.6, up to 0.7 moles per decimeter cubed. Okay, so they look increasingly blue, those solutions. So what you do is you get each of those and you put it into the colorimeter. Okay, and the first one you put in is this one, which is just distilled water, and you set the absorbance reading to 0. Define that as being 0, so that solution is not absorbing any of this reddy orange light that we're interested in. Okay, and you read the absorbance off your colorimeter and you plot a graph which would be something like this. So that'll be absorbance. It's actually a log scale, the absorbance, but we don't need to worry about it. The colorimeter just gives it a straight off. The highest absorbance you can have is really about 2. Okay, this one is 0. That's our distilled water, and we're going to have the concentration 0.1, 2, 3, 4, 5, 6, 7. So that's 0.7 moles per decimeter cubed. And we're going to plot our line. Okay, and it should be sort of fairly linear. It should be linear. So you draw a line of best fit. Then you put your unknown sample. So this would be your unknown sample of copper sulfate. You didn't know how concentrated that was. Incidentally, you probably have a fairly good idea of the approximate concentration by just looking at how blue it was and then comparing it to your set of standard solutions you made up. Anyway, so you put your unknown, you measure the absorbance of your unknown. Let's say it's there, 1.3 or something, and then you extrapolate across and you will get your find your concentration there. So that is how colorimetry is carried out. They occasionally ask that, not very often. It's not terribly difficult, really. Just a few other things about colorimetry. Right, it's usually done in you get a little square test tube. Called a cuvette. And the path length is usually exactly 1 centimeter in those little square things. And that goes into the machine. Quite often, when you do colorimetry, you can add EDTA to your transition metal. And what that will do, it will form a complex, and the EDTA color, the color of the EDTA complex is usually a little bit darker, a little bit stronger than just the metal by itself. So, for example, if you put a little bit of EDTA in copper sulfate, it changes subtly the blue color. It looks more or less the same blue, but changes subtly, but it goes quite a bit darker. And so it will make it more sensitive when you're measuring the concentration. Of course, colorimetry is ideal for making continuous measurements. So say if you're doing a rate of reaction experiment and you wanted to continually monitor the concentration with time. So here's along time along the bottom, and here's your concentration, and you're making something like that. The colorimetry is really ideal for that because you just put the thing in and then take an absorbance measurement every 30 seconds. Okay, so very short video, we'll just leave that one there.